Hi, Michael. Thank you
Hi.
for joining the podcast. And I'm really glad you're here. And for the viewers, Sat Shri Akal, everyone. Um, Today's esteemed
Thank you
guest,
for having me.
absolutely. So, Michael is a key figure in the Kaspa ecosystem, where he serves as a prominent developer and contributor to the Kaspa blockchain. His work focuses on advancing the project's technical development, improving its core protocol, and fostering the growth of its decentralized ecosystem. As a part of his work, Sutton has led the effort to rewrite Caspa's core code base in Rust, which is a move that is aimed to improve the blockchain's performance, security, and scalability. His involvement has also helped Caspa position as a notable player in the space, and particularly for those who are very much interested in faster transaction finality and more efficient consensus mechanisms. So, Michael, thank you for taking out your precious time to be with us. Let's start this podcast with some of your personal questions, man. I think everyone would be really interested to ask you what
Okay.
really inspired your passion for computer science and distributed systems. Were there like any early experiences or mentors that had a lasting impact on your career?
I'm sorry. No, I had this last second thought whether I want to share that or not. So essentially, I wanted to say that I started looking at
Mm-hmm.
even high school. I grew up in an Orthodox, as an Orthodox Jewish, in Orthodox
Mm-hmm.
Jewish education. And I actually started learning like even high school level math only at the age of 21. Yeah, so almost from zero. And there was a year where I catched up um, on like a basic high school uh, knowledge. Um, and then I started a bachelor degree. Uh, what drew me into computer science is just always like a logical. Liked math, and computer science is like the realization of
Mm-hmm.
math in the world, of logical systems.
Mm-hmm.
Um, I don't know. Computer science was a natural choice at that point. Um, yeah. So going above beyond that, about a, a initial mentor or someone. So I did my bachelor degree, and then as a young developer, wanted to join the industry, and I found a job, but I felt really overqualified for what I did. Like engineering at the first stage, it can be like UI systems, and it can be you learn the theory and you have a degree, but then you go
Mm-hmm.
out to the industry and you look at stuff and you're doing like things that you.
So before diving into like blockchain and crypto, what areas of computer science were you like mostly focused on, and what really motivated you to like get into a decentralized world with something like Caspa?
Yeah. So my master's degree, which I started as a result of this experience in the industry where not getting to the right places of where I thought I can contribute. So I realized I need to level up, and that's what like pushed me into doing a master's. And the master's I did with a guy I met. I did a national service in the police at a second department, like as a junior developer, and I met a guy who's doing a similar service. His name was Tal Benoon, and he was doing his PhD. He was younger than me, and he was doing his PhD during this service, and he was like this extreme. He had this extreme ability to be both a brilliant hacker and hands-on,
Mm-hmm.
blazing fast developer, and also a great theoretician. So, and understanding the theory of computer science end to end. So I worked with him, and eventually that led me to doing a master's with him. And
Mm-hmm.
we worked on a master, and his academic career is about
Mm-hmm.
distributed computing, less about the distributed systems where there's adversaries, and more about how to take a computation and run it in parallel on many processors or many systems, and so on. Um, and in that area, we had like two papers doing my master's with him. He went on. He has a research position in Lawrence today. He did his postdoc at ETH. He's a known figure in the distributed machine learning world. How to
Okay.
accelerate, which is very practical and very a hot spot, obviously.
Mm-hmm. Okay. One question. Can you share a specific challenge or a setback you faced in your early career and how it really shaped your approach to problem solving?
So, for instance, so that's not like a problem-solving example, but during my first year in the industry, I tried for instance, to get into Google to work as a developer, and I wasn't like accepted. And even though I had like a great interview, I have no idea exactly why. And and I think that if I would be accepted to a company like Google at that stage, I wouldn't do a master's, and a lot of things that happened later wouldn't happen.
It's a loss
So
for Google, it seems. Yeah.
it completely pushed me to the right direction. Um, there are more examples like that. Like before joining Jonathan and researching consensus, I worked for a data science team in a pretty big company. Um, and things just didn't work out politically in that organization, and the team had to shut down. And that
Mm-hmm.
also is turned out for the good. In terms of problem solving and like facing like a challenge, it's just I can't point that on like something that was. It's just an ongoing pursuit and finding and breaking the problem you're looking at.
It's kind of a
Is
spiritual
the
answer.
most.
Like you really don't know what led you to come into this space. I
Yeah.
think situations came about in such a way that you landed up into this decentralized world. Of course, you were like starting to hop up with a centralized system, and of course, things happened in a certain way. And I think that is what life is. It makes
Yeah.
you end up in the most unexpected places.
Yeah. During my master's, I met Jonathan in this some advanced communication, like networking related course.
Mhm.
Not really about consensus. We just happened to cross paths. He was doing his PhD, I was doing my master's, and he saw me, and then we exchanged a few words in the cafeteria,
Mhm.
and he told me join me, and I said I can't. And then only a year or two later, I came back to him and like asked if it's still relevant, and I can go more on that later.
All right. Let's start to focus on
But there is a
more.
reason why I shifted from parallel computing, parallel algorithms, more towards distributed systems.
Okay. Um, I think we should start discussing the technology specific questions. I think that is something that you would be really excited about. So
Yeah.
let's start with Night. That's uh, that's one of the best research papers that I've ever read when I was researching about you and Yonatan. And it's a great
Thank
work,
you.
man. It's one of the best products that you have ever created. Let's start with the discussion. Night is described as a parameterless protocol, right? Can you elaborate on how Night manages to maintain security without assuming fixed network latency parameters?
Yeah. So I think that the it starts from looking at pure DAG mining. So I
Mm-hmm.
want to say something about DAG mining first, because that's the key.
Mm-hmm.
In a sense, I'll show you that DAG mining hides in it the information about the real maximum network latency, as opposed to any a priori assumption. The DAG
Mhm.
structure itself, if honest miners follow the protocol, hides this information, and that's what allows DAG to to because the information is hidden, so it takes a protocol to extract it. But the key is that the information must be there first, right? So DAG mining is not just. I like to emphasize that DAG mining isn't just another instance of mining. It's um,
Mhm.
the ultimate one, because it's maximizing. We call the earliest mention of DAG mining is in the paper by Yonatan Yoad and Aviv Zohar named "Inclusive Blockchain Protocols." Um, inclusive, I think that's the name. It definitely starts with the word inclusive. And the idea was to be inclusive, like to include transactions from parallel blocks as much as possible. And so, and they call DAG mining the revelation principle. You, as a miner, when you share all the tips of the DAG, when you reference all of them, you actually tell the world exactly what messages you've seen before you created your message. And it's compressed. You only need to point at the tips, and by induction, we can know you came after also all the messages before these tips, as long as there's a path of references. So that's you're actually maximizing. You're sharing with the world with a pretty concise and compressed header everything you knew, your exact worldview at the time of this block being mined. So that's a maximization of information. So in that sense, it's a canonical setup. It's not just another. A DAG is not just another kind of blockchain. It's a canonical thing. And if you are familiar with Phantom or Ghost DAG, so you know Phantom Ghost DAG uses this information. The fact that what's the protocol of DAG mining? The most basic idea of DAG mining is that honest nodes, when they mine a block, they must mine over the tips. They can't censorship. They can't do censorship. They can't not point at something they know of. So they point at everything they know of. And once they find the block, they should broadcast it immediately and not wait. So given that this assumption that honest behavior, what honest nodes do, it's easy to see that there's a simple bound for the number of parallel blocks each honest block has, or the number of honest parallel blocks each honest block has. Why? Because once assume we have this BPS, say we have 10 BPS. In the paper, it's usually called a lambda. We parameterize the block rate by the word lambda, and assume it's like 10 BPS, and assume that the network latency is exactly 1 second. So once you mine a block, there's an average maximum 10 blocks mined in the second before you're unaware of yet, right?
Mhm. Mhm.
And and the second after you found it, there might be 10 blocks created which don't know of you. So so combined, it becomes like the average number of parallel blocks in such a system would be 20, more or less. Or in the paper, you would see 2d lambda. So 2 times the delay unit times lambda, which is exactly 20 in our case. So that's like the intuition. So the width of the DAG, like the average number of parallel blocks of the honest part of it, at least, is bounded. And that structure um, is driven by by the network delay bound.
Mhm.
So GhostDAG uses this structure by specifying the delay bound and extracting from it this k parameter, which is how much we tolerate parallel blocks, um, and it uses that to build like a cluster of blue blocks. But the truth is that the hidden DAG topology and the hidden DAG structure encodes more of, if Ghostdag assumes 10 seconds and the actual delay bound is 1 second, that structure is going to be 20, not 20, not 200.
Okay.
So there is this information about the actual delay bound in the DAG. So DAG Knight thrives and tries to obtain this knowledge.
Hmm. Okay. So, I was reading when I was reading your paper, there was a very interesting mention on the knight's tolerance to 50% Byzantine fault threshold. What makes this security threshold achievable in Knight, and how does it really compare to other consensus mechanisms?
So you are referring to the fact that usually protocols which do not assume the delay bound cannot achieve 50% Byzantine tolerance. So there's a famous impossibility result. And usually these protocols which do not know what the delay bound is are called protocols operating in the partially synchronous model. And there's a famous impossibility result that shows that there cannot be, you cannot achieve consensus in this setup if the attacker has more than 33% of the power. Uh, In those, in the classic BFT setup, it's more like a F out of N, like you know exactly the number of participants, and you're saying that the attacker cannot have more than a third of that. In the proof of work setup, it's more about the fraction of computational resources, but it's the same idea. So all impossibility results regarding the partially synchronous model actually use the fact that the protocol must terminate without knowing the delay bound. This is actually, I'm going into a delicate area now, and actually not even completely finalized on how to communicate it in the best way. But so all the impossibility results are all about the fact that the consensus protocol must terminate with a decision. Usually in the classic setup, the consensus protocol only needs to get like a 0 or 1 decision. It's not about an ordering problem yet. You don't need to order events and have them converge, but you actually only need to get one decision. So the protocol must terminate with a decision. So here's exactly where the fact that the protocol participants don't know the delay bound, and if the attacker is powerful enough, say he has 40%, he can simulate different worlds to two fractions of the network. And he can do something with, he's a 40% and he's communicating with one part of 30%, and he's doing a different show for the other 30%. And he's showing them both different worlds. And for one of them, it seems like the delay is very short, and that group sees like it sees like a 70% agreement because with the attacker it's 40 plus 30. So it seems like a sufficient majority, overwhelming majority, and um, and it can act as if the delay is very short. And if the protocol is unaware of the real delay bound, it must make some decision. So it must be, it has a way to mislead it. And it can simulate this slower delay to two of the groups, even though the real delay is much higher and they don't hear of each other because of the real delay. So all impossibility results rely on that. Here we actually say the protocol participants, the nodes, the miners, the canonical ordering running, like if you run the Dagnite ordering, is unaware of the delay bound. But the clients who would want to make a decision about whether this transaction was accepted with enough enough probability, they do need to have a belief on the delay bound. So the protocol is parameterless in the sense that the canonical consensus participants don't need to know the delay bound. You don't need a hard fork if you want to change the delay assumption. They all run without knowledge. And the client must apply his real world or real time belief about the bound now in order to make a termination decision. A termination decision being, okay, this transaction was accepted, I can give the car to the customer, right? In that sense. So yeah, we're bypassing the impossibility result by It's like it's gaining part of the attributes of the partially synchronous setup because, um, in a sense, you can still say the sentence. This protocol can operate without knowing the delay. So that's like how we can achieve 50%.
So, in the last question, we just discussed about the Phantom's K cluster approach. And could you just walk us through the motivation behind minimizing the K value for selecting a cluster?
Yeah. So I want to, at this point, I think it's a good point to share the frustration. What problem, what like a whiteboard drawing was like, this can't be. There must be a better way, even better. Like Ghost is brilliant, but there must be an even better way. And that's the fact that when you look at Ghost because it chooses, for instance, it takes like an a priori delay bound. And it must take like a margin. So we put something like a 10 seconds delay bound. And for instance, in mainnet, we have K set to 18. While usually, if you look at the DAG, you'll see 2, 3 max width. So you have to take into account this worst case scenario. Okay, what it means, but is that the protocol allows anyone to operating within the 10 seconds delay bound. Anyone that it isn't, that is not pointing at the blocks from the last 10 seconds, or is not publishing itself for 10 seconds, because uh, the protocol treats him as honest, as doing uh, reasonable. He's acting according to the protocol assumption about the delay. So even though he is violating the protocol rules in terms of mining, he's not doing honest behavior, but the protocol has this tolerance. And so the actual delay unit of the system becomes this 10 seconds or 5 seconds, the 18 parallel blocks unit. And that affects confirmation times. But if you look at the DAG in real time, you see that it doesn't require. So you're like, okay, I'm seeing now, let's take it to the extreme. Say that the delay in the system is 100 milliseconds at 1 bps. So you'll see a chain always, with almost always, right? So you see this chain. Why do we have to wait for confirmation for 18 seconds or for something equivalent to the delay bound we assumed a priori? Why do we allow the attacker to operate within 10 seconds delay bound while we can see it with our own eyes that the DAG is converging and in fact is more connected than that. So the idea of the DAG night optimization was like to say, okay, obviously you want to maximize K clusters. You want to find the K cluster which is the largest because that represents like a connected subset of proof of work where you want to follow. And you want to take the larger one because it means like it won a block race. So the largest K cluster, given a K, taking the max makes sense. Just like the longest chain rule is like a max of the zero cluster.
Mm-hmm.
The longest chain is the largest zero cluster. But on the other hand, we don't know, we have a protocol which does not know what the delay bound is. So he wishes to maximize connectivity, to choose the subset of blocks which are the most connected. But you can't go if you just choose the most connected, which would be a chain, you would lose on safety. You would obviously, in some cases, just take a chain out of a wide DAG, and that's only a fraction of the proof of work. So any attacker, 20% attacker, would be able to outweigh. So so the idea was to find a criteria where we look for the minimal K cluster, but it has to be a K cluster which has some property. So the property we found was, let's find the most connected, meaning minimum K, which is large enough to cover at least 50% of the DAG. And that definition captures in the best way possible the idea of most connected and large enough, because it exactly goes with the honest majority assumption. In a way, think of it as a machine learning algorithm trying to identify the honest cluster or a sufficient portion of the honest cluster. So it's like not a dichotomic world where blocks are either honest or malicious if they're in the bound or out the bound, but more of a scale. The more connected you are, the more.
Okay. And the protocol prioritizes performance based on the worst case latency an adversary might cause. Could you discuss the implications of this choice, especially in terms of transaction confirmation time?
So that's worst case adversary, as opposed to just real world latency, as opposed to just observing what happens. And um, so a protocol which operates with the network delay it sees is called responsive. And in a responsive protocol cannot be 50% resilient. There are impossibility results within proof of work that show that you can't be responsive to the actual delay. The point is here to be secure in the worst case adversary bound, even though it's unknown. The choice is because we want to be 50% secure, so we can't. So designing protocols which are responsive, which is just not is out of the picture. Like our framework was, we must be 50% resilient, and then within this, let's find ways to be more flexible and less strict and less fixed on some a priori assumptions.
Hmm. So the Knight builds on the proof of work model, but includes several modifications. Could you elaborate on how these modifications affect its scalability and security, especially in comparison to Bitcoin's proof of work?
So modifications meaning you're saying it's proof of work, but it's just different, right? It's
Yeah,
not
absolutely.
exactly doing the same.
Hmm. Exactly.
One example would be that the in Bitcoin there's a random walk analysis. When you're asking about like what's the probability of, I see it already six confirmations, like six blocks above my block, and we're asking what the probability there is an attacker with a hidden chain of seven blocks. So the probability for that would be like it's a skewed random walk. It's a random walk from starting from the origin zero and biased to the honest side because it has 51%. So you flip that. So the point where you have sufficient probability that the random walk has shifted left is where you can confirm transactions. So in a sense, introducing K, also Dagnite has this dynamic K, means that the analysis of the random walk starts with a skew. You sometimes need to give the attacker some head up advantage of in the order of K, and because he can use K honest blocks and still seem legit. So he's like skewed, and then the random walk analysis starts from there, but eventually it still shifts left. So, and that's where Dagnite is tighter for confirmation times because the K is not an a priori number, but the real world adversary bound. So, so the client can say, okay, I believe the network delay is a second, and I don't believe an attacker can change that. So, according to my belief of the network, 1 second is an upper bound. So I can use that knowledge to tighten my confirmation times. So that's like one example where analysis is different from Bitcoin proof of work. There are others. It's more it's a
Mhm. Let's discuss the algorithmic approach for DAG ordering that diverges from the classic linear blockchains, right? Could you detail how this ordering system works and how it really impacts the transaction finality?
so that's a I think it's a good question. Um, and I usually really when I explain it, I try to decouple the Ghost DAG specifics and the DAG Knight specifics, and explain why DAG ordering is based on some black box chain selection, a chain being like a some chain within the DAG, and it um, drives the ordering from that chain. So, in a very the most concise way I can explain it is think assume that each block has like multiple parents, right? But he has some kind of function that for selecting one specific parent, a deterministic function for selecting one specific parent. So if you had a DAG starting from a genesis, and then each block has many parents, so it's this interleaved structure. But if you take one edge, it's essentially it's choosing one edge from each block to one of its parents. So what you get is a tree structure, actually. Tree structure, um, no cycles, obviously, but also it has a tree. It's a tree. So, and if you imagine the virtual block, which is the next block to be mined, he also can apply the same function and choose one of the leaves, right? One of the tips. So you would be able to start with the virtual block and have a chain going down to Genesis, right? If you had this black box function f for selecting one. Now, if I take this, you can view this chain as and now you can order the DAG in layers. Each starting from the, so you got this chain. Now, starting from the bottom, you let each chain block order the subset of blocks it added that weren't yet known to its parent. Like in DAG terminology, it would be the past of the block minus the past of its selected parent. So it's a merge. We call it a merge set because it's kind of the blocks you merged into the structure. So you inherit the ordering from your selected parent, and you order the merge set. So you get like a layered uh, um, ordering system. And if the chain, if it happens to be that the magic function helping you select a chain, a selected parent, which induces a chain, eventually, if that function is secure in the sense that the change doesn't change only at the top, so the ordering implied by it, induced by it, also doesn't change. So that's how you can. So now you can play with the chain selection being in a Ghost DAG now, and even if we change it to DAG Knight, most of the code base doesn't rely on the specifics of Ghost DAG for the ordering and for UTXO state building and all that. So I don't know if I answered the part about transaction confirmation times. Maybe you can make it more clear.
Hmm. I just wanted to like elaborate how the order system impacts the transaction finality. That is something that I think everyone would be really interested to know.
Right. So if the ordering is induced by the chain, and the chain is guaranteed with high probability to only change up to a suffix, but most of it is already stable, so everything ordered by that suffix is already stable as well. So no new transaction can enter the ordering before a previously accepted transaction. So even though we're looking at this confusing world of DAGs, of a DAG, and there's blocks, and blocks can have parallel transactions which conflict with each other. But as soon as the ordering stabilized above some transaction and was accepted, meaning there were no transactions before it in the ordering that made it invalid, and you know that that part of the ordering is not going to change anymore, so no future transaction can insert itself before and make that transaction invalid. So the finality of the convergence of the chain And the ordering implied by it is what gives you security for your transaction, even though there might be conflicts.
Hmm. Let's move on to the next question. So, could you explain how the dual min-max approach to cluster selection helps Knight balance between safety and liveness in the consensus process?
Yeah, so I touched on it to some degree. So the min max is like what I mentioned, like the max k cluster, and finding the minimum k such that the max k cluster is at least 50%. And the real definition in that's like a more abstract optimization. The real the actual Diagonite protocol searches for a stronger property, not only 50%, but what we call a UMC, a uniform majority coverage, that each block in the subset um, has 50% over it. It's a stronger assumption, a stronger property, which we realized is needed for a few reasons. So the min max is like I said, if you would just minimize k without any constraint being that the k cluster is at least 50%. If you just minimize k, you hurt safety. Why? Because you would choose okay, you would choose a zero cluster, a chain, and that chain can be only 10% of the hash rate of the honest network. So 11% attacker would be able to attack the system. And if you just take the largest k without uh, thinking too much, so you hurt the confirmation times, like I explained about ghost DAG. So the min max aims at finding the sweet spot. It's also it's not only it's an interesting part. It's not only adjusts itself to the actual delay bound, it also adjusts itself to the actual alpha power. Like if the attacker is weaker, you can actually find some. You can if the attacker is only 5%, we can actually find that a zero cluster might be enough. So we dynamically can choose the width we need in order to counter this attacker. And so if you as a client assume a weak attacker, you can even reduce the K you believe is needed even more and confirm transactions faster. So it's dynamic also in the sense of adapting to the attacker power, which is an interesting observation. But that's like the idea of the min-max. It's like, okay, I'm seeing this chain now, so why do I need to give any K for confirmation times? I'm seeing this as a chain now, so I can reduce in real time to block to Bitcoin security if I see a chain in some cases.
Mhm. Let's discuss a bit about the confirmation times and how it remains optimized even under high latency conditions. Are there any specific scenarios where confirmation times may be notably affected?
So part of being like not having any assumption. So in Ghost DAG, if you assume 10 seconds, but there's some disruption, and the network actually has 100, takes a minute to propagate blocks. So you actually would not be able to to confirm transactions at all because the K cluster, the 18 cluster, would be only a fraction of the real DAG would turn out to be like very, very wide, like hundreds of blocks in parallel. And the 18 cluster would be only like a very small portion of it. So you would lose security, like an attacker could easily. So with the in the synchronous setup where you have an a priori delay bound, if that breaks, then you can't confirm during that period. So it does recover. Like all proof of work protocols, including Bitcoin and Ghost DAG, would recover from such a phase. Once delay goes back to normal, there's going to be convergence. There's, we're going to converge about over one of the chains, one of the DAGs, one of the longest, largest K clusters. And from there on, we're going to be back to being able to confirm transactions eventually. So that's like a self-stabilizing property. Um, I lost my point. Where was I? What was the question?
So the question is, are there any specific scenarios where confirmation times may be notably affected?
Yeah. So but in Dagnite, if network conditions go bad, you can still, um, even if it takes suddenly 10 minutes, you can still confirm as a function of those 10 minutes. But if latency is bad, confirmation times are always proportional. You cannot go better than latency. So the point is being able to adapt.
Let's move on to the next question. So, in case of multiple cluster candidates, when they have similar rankings, how does the tie breaking process really work, and how does it really ensure both security and efficiency?
The tiebreaking is like an advanced topic in this paper. I don't know if we have enough context for it. Um, and I'm even trying to simplify this part still. But the idea is you want to, even under what we call a visible conflict, like if the attacker is not hiding but is actually trying to maintain a parallel chain, and he's like, it's a sometimes called a balancing attack, which isn't like it's not a safety issue. It's not a safety attack because people can see there's something going on. But you need to be able to have the for some k bounded k, you need to be able to show that the k cluster is still growing at least at the rate of 50%, because that's like the property that the protocol is searching for. So you have to show there's sufficient growth. It's called the chain growth property. And in order to, in some cases where there's might be confusion, we noticed that the tie breaking rule has importance, special importance, and in those cases it actually does some kind of a free search for the maximal K cluster without any constraints, and uses that as an oracle for understanding what side to choose. And that, it's not even about security yet. It's just about ensuring that always there's growth. The K cluster is always growing fast enough.
Hmm. One last question. Do you really envision Night being used for applications outside of traditional cryptocurrencies, such as supply chains, logistics, or IoT, Internet of Things?
Um, I don't know. Like people ask why go 10 bps. So there are answers, like being a more responsive. That you want a blink of an eye response from the network, and future designs related to MEV, which will utilize the parallel block structure. But the for me the first answer is the world will find out. Like, it's just like a hardware chip development. You try to make things faster, even though you're not sure about the use case or what's going to happen. But the minute you develop something that has orders of magnitudes more frequency, is responsive, and can it changes the surface, and people can rethink stuff about above that. So my answer is I don't know, but I believe yes. I believe some other areas might eventually. There's a longer answer to this related to the fact that scalable protocols such as GhostDAG and DAGNITE, the fact that they allow parallel blocks is actually a game changer in the area of game theory dynamics. Because game theory dynamics now happen between parallel blocks within the latency unit, within the second, 2 second time period, there are parallel blocks which don't know of each other. So as opposed to security where you want to maximize like the knowledge of it, blocks of each other, here you sometimes wish to maximize the fact or to use the fact that they don't really know what the others are doing. So that creates a healthier fee market, and it can be used to build auctions mechanisms above where the parallel miners compete on something, and they each bid and give the user back more money because they use his transaction to extract value from a smart contract. So this scalability is actually opening doors no one imagined before, I think, and I think it's extremely significant. Also, an anecdote is um, it's very interesting that in Rust we've seen it. When blocks are in parallel, they actually are independent by definition, right? They were each created independently. They don't know of each other. Their state and their validation doesn't depend on each other. So there's a point where you have a 16 core machine. If the dagger is more wide, it can actually process it faster. It can scale up the validation times, which is an interesting balance, which can go on.
Hmm. I would really like to thank you, you and Jonathan specifically for giving such a research paper to the world. I think it is a milestone in the human race, where I think everyone should read what you guys have published. I would like showcase this research paper in the description of this video as well. It's a beautiful piece of art, I would say. It definitely gives a beautiful insight to the future world of blockchain, and not only blockchain, I would say a lot of things can be built on the top of this beautiful algorithm that you guys have given to the world. So thank you, Jonathan, and thank you, Michael. Let's move on to the next section of this podcast, especially.
I have a
Uh-huh.
special relationship with him. He's both a mentor, and we have a relationship where I feel like I have my contributions to into the way I think and engineering knowledge and the combination of worlds, and the clarity. Sometimes we try, but we have like a special relationship in the fact that we can together deep dive and we complement each other in a sense. Um, and he's a great mentor, and I cannot be more thankful to being able to work with him so closely for the last 5 years. It's very special for me. I appreciate him.
Absolutely. I hope we can get him to this podcast as well, and maybe we can deep dive into more such difficult questions. I think technical aspects of this research paper and more work that you guys have already done. It's something that should be noted around by the people in blockchain, and I think it's something that we should discuss more. So let's move on to the next topic, where we will be discussing your role in the rewiring of the entire code base. So it's a major step, it's a major milestone when we look forward, say 10 years from now. I think this will be one of the major milestones of Caspa, where the whole code base was rewritten in Rust. So, what led you to choose Rust as the language for Caspa's implementation? Were there any performance specific or safety advantages that Rust offered over other languages? I saw that you changed the entire implementation from Golang to Rust, and you are the one who pioneered the whole uh, rewrite. So, tell us more about this.
Yeah. So the rewrite, the goal was to if so the first the Go version of Caspa was developed with the mindset of achieving something like 1 BPS, and they had so many challenges conceptually designing many sub algorithms. We had many challenges. I'm saying they because I wasn't, before mainnet launch, I wasn't actually so much involved in the actual coding. I was involved in designing some of the algorithms, but yeah. So that's why I said. So they had so many challenges. So they did the big step of designing the system, but eventually, when we mainnet started rolling and we got this positive feedback of acceptance and interest. So I was thinking, what can we do? Taking such a system to 10 bps or dreaming of 100 bps actually is a point where you have to write a system with the performance oriented mindset for that. So once you've solved all the conceptual problems and the algorithms, you can take another step and actually maybe Go was, I'm not sure, but perhaps Go was the right choice for that phase because it frees you from worrying about memory, for instance, and a few things which are uh, uh, obviously part of being a higher level language. Um, but once we realized we want a performance oriented design, so it made sense to switch the language because writing something performance orientedly is a shift in mind. For instance, like the whole consensus area of the code base in Go is monolithic. It actually only one thread operates at a given moment, doing header validation or UTXO state computation, always under one thread. So doing something like that when performance oriented means like shifting gears and doing a different way of thinking. And so it made sense to switch to a language. My first thought would be actually CPP. I had much more experience in C++. Doing my master's, I developed high performance algorithms in C++ and CUDA, and so I knew my way around there. But when I heard about Rust enough and heard about it from people like Elichai and Anton, and which had like a lot of experience already, it actually I realized it has the performance gains, but it also it has all the advantages of a modern language without all carrying on its back all the scars and the wrong designs and like CPP has. So Rust is much built like a modern language. It has a modern build system, and like you mentioned, safety mechanisms, which are I wasn't aware of their strength at the time actually, but now I can say much more about it. Like, yeah, actually feels if you look at Rust deployed to mainnet, there was not one bug um, that I know of since we deployed Rust to mainnet. So we had a long stability phase, but the fact you can continue developing the system and it feels safe has a lot to do with the Rust memory safety and actually cross-thread safety, which the mechanisms for cross-thread safety are also embedded into the language very well.
Hmm. Since we have talked about safety, how has this implementation, or I would say re-implementation, improved Caspa's performance and security? Could you share any specific metrics or insights gained from running Caspa on Rust?
So the performance is I'd say even if you took Rust and run it on a single core machine, you probably have 2 to 3 speed up over Go because Rust optimizes compiler optimizations, rolling up or many basic operations are not abstracted, but the compiler actually optimizes them through generics and many other mechanisms in the language. So also we did like many optimizations unrelated to parallelism. Even before talking about parallelism, we optimized many subcomponents, especially when you scale up to 10 bps. It's not anymore only about doing something faster. It's actually different complexity variables kick in suddenly. You scale up to 10 bps, sometimes something becomes quadratic in the average number of parallel blocks if you don't think about it. Or you suddenly have you write as a DB and you notice that the complexity of the write becomes quadratic with the size of something, And with 1 bps it never hit. It was marginal. It was and here with 10 bps it becomes like a bottleneck, and you have to optimize the algorithm. So, so I think Rust would give you like 2 to 3, even 4 to 5x over Go purely, even if you take it 1 bps. You cannot run 10 bps on Go; it just will not work. If you try it, it's not only about changing the consensus parameters; it's just not going to work. Um, so it's not only faster, it's enabling something that couldn't be achieved without it. And when you add to it parallelism, it becomes like a complete beast, because it scales to the cores, and it runs header validation in parallel to body validation and in parallel to state computation. And within headers, it does validation to each parallel header in parallel, and it can do a lot of parallel stuff. Uh, and the trick part is managing like the storage correctly with all this parallelism, obviously. It's not easy to do consensus sensitive code with parallelism, because consensus sensitive code is so sensitive to every condition. You have to have all the nodes agreeing on something, even though they might get the events in different order, and the different order they got the events with the parallelism creates some
It's very difficult to understand. Yeah.
uh, yeah. So writing consensus code, which is also parallelized,
Mhm.
is a challenge. And
Since we're discussing about parallelism, let's move on to community contribution. So, how do you see Rust impacting the future of Caspa, both in terms of long term maintainability and community contribution? Are there any ways you envision Rust enhancing Caspa's adaptability or its appeal to a broader developer base? Because Rust is a relatively new language um, in comparison.
so I don't need to vision it or imagine it. I can speak about facts and what happened. So in a sense, I can say that the most important, maybe the most like maybe underrated uh, benefit Caspa has from the rewrite to Rust is not actually only the performance or the way the system behaves and can scale now, but the fact that many non-core developers participated, and if we had quite a few like, and it's quite a few, is 4 or 5 people who made major contributions. That's like the world, because it's scaling the task force of development for Caspa. So people who actually rewrote something in Rust now, they recreated it. They know exactly how it works.
Right.
There's some knowledge you cannot acquire without trying yourself. So that fact alone gave us more people who know the core. So they don't know all of it yet. Some of them are more into focusing on some areas. Some of them try to get the broad picture as much as possible and read every paper and every theory and everything, which is specifically, I have a quarter of stuff in mind. Which is, he's like a guy who, that's his nickname, quarter of stuff, and he's like anything. He doesn't leave any stone untouched. Like he lifts every stone and looks under it and tries to understand what's going on and get the broadest knowledge he can have. Um, and that's like the biggest, maybe the biggest win of the Rust rewrite. And I often like wonder what would have happened without this initiative of rewriting Kaspa, and I don't know what the answer would be, but I think it has a major place in what Kaspa is today.
Of course it is, man. Last question before we move on to some of your personal questions, maybe, where I think many of.
More
Yeah,
personal
absolutely.
questions.
Everyone wants to know more about Michael Sutton. He's not absolutely visible everywhere. So, as a both researcher and a developer, how do you balance theoretical considerations with practical application when implementing complex blockchain protocols in Rust? Is there a particular challenge that you faced where research and development viewpoints intersected?
I think first and foremost, like I come from. I always speak about
Hmm.
latency. So the fact that if you have if you know the classic high tech, you have a team of algorithm like algorithmic people and a team of developers who don't know exactly what complexity means, maybe, and then the communication between these two teams has a large cost. So once you have a person which is has a leg and hand in both worlds, some ideas can circulate much faster.
Mm-hmm.
So you get like a faster feedback loop between okay, we know this, I know this theory, and I know what the wallet needs, and I
Mm-hmm.
know how to go back to fix the theory in order to improve that edge case where usually the theoretician wouldn't. It would take much more time to communicate, and so that's one thing. And I think this fast feedback loop sometimes enables things that wouldn't happen without it. It's not only like a time thing. It's like at some point, sometimes you need, sometimes you actually need, when you have a discussion about the design, it benefits when you have someone that isn't proficient in all worlds, because it helps clean up the discussion. So when sometimes the fact that I have both views is not always the advantage. If I have Jonathan around and he's like saying, no, it can't be. You're going into too much technical zoom in, which are not the core of the problem or are obfuscating what we're talking about. Let's focus. So it goes both ways, but uh, it's an interesting role to have. And yeah, when you understand the theory, very good, and you try to implement it. So there's applied research, which is very hard to do if you needed to connect uh, two people with the knowledge. So I think it helped me, for instance, in the Rust rewrite, like do things very fast, like doing the majority of the work with Oli at the time, doing a large portion of the work like it fast. So that's like
So let's now jump to some of the best personal questions that you can work on.
mhm.
Everyone now knows about Shai's cooking skills because of our last podcast, and let's go ahead with you and let's ask you, what do you enjoy when you're not working on Caspa or writing code or doing some algorithms? Any hobbies or interests that people might not expect from a code developer?
Hmm. First of all, I have a family. I have a wife, three kids. I have uh, ranging from 12 to 2. So there's a baby around. Um, and I love them. Besides family and there's a lot of cultural stuff, music. I play basketball. Perhaps that
Okay,
would be a surprise.
that is a surprising thing. Yeah.
I'm a decent shooter.
Oh, that's cool.
Yeah.
Anything else? Any other hobby? You do you like to travel? Is that something that you're really passionate about?
So it's not so easy to travel with kids, especially at the younger age. Um, I'd like to travel more, but sometimes it's not the time. And I would travel more for Kaspa related stuff. I recently just came back from Ireland from the KII conference where I gave a talk. But if I do
Hmm.
that too often, I wouldn't be able to progress. So I have to not go, even though I am shifting my mindset in terms of like understanding that knowledge passing on is becoming more and more important, and
More
we
important,
must
yeah.
scale. But I still need to balance it with actual progress of development and research. There's a lot of research also going on. So it's a combination. So traveling is something I'd like to do more, but doesn't happen enough. Also, not so easy with the current situation here. Um, Music, good music. Chess was a hobby once, and don't find the time for it now. But and I like to read books,
What kind of books?
all kinds of books, like philosophy, story, fiction books,
Hmm.
novels, whatever. Just good books. in Hebrew or English. Um, I've always been a reader. Yeah.
Hmm. Let's talk a bit about work life balance. The blockchain space never really sleeps. It's a 24-hour market, right? Do you have any personal routines that helps you to unwind?
So we've chatted about it a bit. So I have this amazing force something I always must take this a pause during Shabbat because I'm an Orthodox Jew. I keep Shabbat, meaning that on Shabbat I actually don't touch any electronic device actively. Only we use light and stuff, but we don't actively don't touch a computer. I don't look at a phone. So that disconnection is amazing for me. It gives me even in the most hectic times, I still have to take this pause and I actually can disconnect, be with the kids, the family, and yeah. I mean, at the first year of Kaspa, was like 24, 25 hours you're offline and you go, come off online and you're like, anything could have happened, like an attack, a bug, a
Exactly.
crash. So
Uh,
nowadays it's
Absolutely.
more calm, but
Back in the early days, if you were gone for 1 or 2 days and something crashed and everyone needs Michael, so how do you like manage that?
so I wasn't the only one. There were also other co-developers, and they just knew that if it's Shabbat, I'm not around. So I think I kind of stepped up more during normal days because of it. But maybe, but
That disconnection is somehow very necessary to help you rejuvenate for more
yeah,
work, and I think that that helps a lot in the longer run.
yeah.
On an ending note, Michael, I would really need you to give an advice to any youngster who wants to become like you. Uh, anything that you would like to tell new budding developers who would want to create something for the community? How how do they really become like Michael? What's your advice for them?
I think I mean obviously talent helps people get do stuff, but I find in my life that belief is the most important precondition. One must believe he can do something, otherwise he usually will not achieve it. Like sometimes it's more important than talent. Like you actually need to believe, and I think what drives me also is a desire to affect the world, to have a to make a difference in something, to understand the truth in nature better. Like research is about this problem you're looking at, and it seems you're frustrated because and you have to go into the very basic elements of it, of the problem at hand, and break it into the logical units, the most basic ones, and then sometimes you gain the clarity, and that clarity is like the yeah, we walk in life between those moments of clarity. We're mostly in the dark, and here and there we get this lightning, and that's worth everything to me because when you are able to put a flashlight on something and light it and make it more clear, so that's something that drives me. And so I think you need, in order to achieve stuff, in order to find solutions to hard problems, you have to believe and you have to have this sort of driving force.
Michael, how do you maintain this modesty, man? Like, I don't have such an experience. I have met developers who just forked something from the Uniswap protocol and now they have this thug life attitude. And here is this guy who entirely wrote the Rust implementation of a big blockchain and being very modest about it. Like, how do you manage this modesty, man? Like, on a personal note. Do you think philosophy helps you to become modest? Do you think your connection with God or your disconnection during your Shabbat?
Maybe, yeah. Being a believer obviously has a believer in God. Um, Obviously gives you some modesty, I think. I don't think I suffer from the syndrome, from the imposter syndrome. I don't have that. I'm aware of what I can do. Um, it's probably better if others appreciate it than you praise yourself. I don't know. It's just I know what I can do, but I think it's about approach,
Hmm.
and more people can adopt more of that approach. I often there's a saying in the Jewish Mishnah, which is
Hmm.
like the text the Talmud is based on. In the Mishnah, it says where there's no person. Um, the saying is "Makom she'en anashim hiya ish." Be a person where there's no people. So it's sometimes
Hmm.
it's also sort of about humanity. Be like it's important to give the role of the human to be the human where there aren't others. Um, but
Hmm.
I ask this question like there's so many places where there's no where there's lack of people who actually operate in that space and try to really innovate. And there's so many places where there's room for someone to contribute. So I wish more people join. I think Caspa is an opportunity to research, to new research spaces now, which are evolving above it. Um, Especially like you could say maybe that the consensus layer is the foundation of Caspa, and Dagnite is like one of the final step towards perfecting that layer, perhaps. But now the surface above, where there's game theory dynamics, smart contracts, and more economic activity, is where a lot of research can happen, and there's so much to explore. So more people should join, and um, and it's also a unique opportunity for developers who like high performance, who like performance, and actually can help scaling up. Because now, once the protocol removes barriers from scalability, the only barrier is hardware. And when you
Hmm.
once you learn how to use parallelism and and can use also cheap hardware to its extent, to its maximum. So that's an interesting place. Also, it's a
Hmm.
disciplinary spot of high performance systems and and consensus and a financial layer for the world. So it's a both. It can be both a call for researchers. There's a lot with the research, and for developers who want to join this very interesting spot where you don't own, and you don't always. You're not only like saying, okay, let's do many computations. Let's assume this machine that has uh, so much resources. It's a ever going quest to optimize using the most cheap because we have a decentralization value and we want to scale. So finding the balance is always you can always do a little better, and it's a very interesting spot to be in. Um, and that's like the Rust, and then there's research where there's a lot to explore now. So
Hmm. I think that was a very interesting podcast, Michael. On an ending note, I would say a tree which bears a lot of fruits eventually bows down. And I think you are a very right example to the world. I think we need more people like you for the world, who really understand the value of modesty, of giving back to the society, who value the traditional aspects of life, because I think that is what makes us human. And it's better to be more human because we see less of that nowadays. So thank you for giving your precious time to us, Michael. It was a pleasure talking to you, and I hope to do such more conversations with you. Maybe Yonatan in the future. Again, Shy, you guys are amazing.
I'm pretty sure we can do it. And you were such a pleasant host and such great, deep questions. So thank you for the chance to answer these questions.
Thank you for your time, Michael, and we'll see you soon again, man.